Today we are talking about the energy balance of agriculture. This lecture is based on chapters 7 and 17 of the book Principles of Agronomy for Sustainable Agriculture. Chapter 7 is the chapter dedicated to the energy balance, while chapter 17 is that dedicated to tillage. We have to ask ourselves why apparently agriculture shows such a low energetic efficiency. In this table, we show the different components of the energy balance of a field with an intensive olive orchard that covers around 40% of the ground. Here we show the available energy at different levels and how this available energy is spent, what we call losses. This is an orchard in southern Spain, Córdoba, where the total solar radiation during the year is close to 6,000 megajoules per square meter. That amount of solar radiation is partly reflected, more than 1,000 megajoules per square meter, and part is lost by radiation emission with more than 2,000 megajoules per square meter. The radiant energy not lost, what we call net radiation, is roughly 50% of the total solar radiation. This amount of radiant energy available, this net radiation, is spent partly in evaporating water, LE, flux of latent heat, more than 1,500 megajoules per square meter. A large part is also invested in heating the air above the orchard, more than 1,000. In the end, if we subtract evaporation and air heating, we come up that only a small fraction of the solar radiation that we had is accumulated as energy in photosynthetic due to the photosynthetic process. But also, for those only 40 megajoules per square meter that we have accumulated in chemical form, 50% is lost by respiration. So, the amount of energy fixed, the net photosynthesis, is only 50% of that, in other words, 20 megajoules per square meter. Of those 20 megajoules, a large fraction is invested in growing vegetative parts of the olive trees. So only 12 megajoules per square meter remain for harvest as olive fruits. If we remove the residues, we have only a harvest of oil equivalent to 7 megajoules per square meter. So looking at the whole picture from a high value of radiant energy that we have, we accumulate very little in the harvested fraction due to agricultural activity. But this low efficiency is basically due to the use of the radiation balance, reflection and emission, and then the partitioning of net radiation between evaporation and heating the air. So finally only a small fraction can be dedicated to photosynthesis. Now we will look at the energy balance of the farm by looking at the difference between the outputs of energy from the farm and the inputs of energy excluding the radiation coming from the sun. We can classify the inputs of energy to the farm according to different criteria. Here we will consider that we have inputs that we call direct because they are used at the farm at the time when they are consumed, and we have indirect inputs that is the amount of energy used in producing the inputs. So usually the indirect input energy is spent out of the farm and before the agricultural activity, while the direct input of energy is used at the farm at the time of the agricultural activity. This is typically the use of fuel for the tractor. We can also consider that some inputs may be called fixed if they do not depend on the input levels or the yield that we get. On the other hand, we can call variable those inputs that the inputs of energy that depend on the input levels or the yield level. For instance, if we consider sowing as an agricultural activity, we first need to move the tractor and the drill, and the energy used for it, usually coming from fuel, will be direct because it is spent at the time of sowing, and also it's fixed because it doesn't depend much on the expected yields or the amount of seeds that we're gonna put. So the energy in fuel would be a direct fixed input of energy during sowing. But before we can sow, we need to buy a tractor and a drill, and the energy spent to manufacture and to maintain the tractor and the drill would be inputs of energy that are indirect because they are performed before the agricultural activity, and they are fixed because they do not depend on what will be the use of this machinery. Finally, to sow, we need to use seeds, and the energy spent in producing the seeds would be an indirect input because it is spent before the agricultural activity. Before sowing, we need to produce the seeds, so it is indirect, but also it's variable. Why? Because the amount of energy spent in producing seeds depends on the amount of seeds that we gonna use in sowing. In other words, it will depend on the sowing rate. With the same criteria, we can classify the energy inputs in other agricultural operations. We have already seen that for sowing we have a fixed direct component for fuel, we have a fixed indirect component for machine and tractor, and we have already said about indirect variable for seeds, but we could also add pesticides or fertilizers during sowing. Tillage operations will require a direct fixed fuel, and they will also require indirect fixed energy for producing the tools and the tractor. In the case of irrigation, we have a direct component, but it's variable, usually depends on the amount of water that we apply, and this will be dedicated to fuel or electric energy for pumping. But for irrigation, we also have a fixed indirect component that corresponds to manufacturing the irrigation system. But also we can have an indirect variable energy cost due to the desalination and transport of the water to the farm. For pesticide applications, we will have a direct fixed component, an indirect fixed for machine and tractor, and indirect variable for the amount of pesticides that we apply. For harvest, we have the direct fixed component and indirect fixed component for producing and maintaining the machine. The same goes for processing the yield, but in this case we will have a direct variable component that will be proportional to the amount of yield that we get. If we go into more detail, first let's see how can we calculate the energy required for irrigation. In this equation we have that the energy required is proportional to the density of water. G is the acceleration of gravity. Capital A is the seasonal applied irrigation. Mu sub P is the pump efficiency, while mu sub M is the motor efficiency. The pump efficiency may lie between 0.6 and 0.8, while the motor efficiency will depend on whether the motor if we are using diesel or an electric system. For diesel, mu sub M would be 0.4 and for electric would be 0.9. Then we have here capital H, lift, is the energy required to lift water, and this is approximately equal to the water table depth. Should be almost close for surface water. And then here we have HO, which means the operating pressure of the system. It should be between 10 and 25 for drip irrigation and between 30 and 40 meters for sprinkler irrigation. So first we have a component that depends on the pumping cost of water. Then we have two other components, energy indirect fixed and energy indirect variable. The energy indirect fixed is that required for manufacturing and installing the irrigation system. This is usually between 7,000 and 9,000 megajoule per hectare per year for a sprinkler system, and as high as 13,000 megajoules per hectare per year for drip irrigation. The energy indirect variable refers basically to the energy required for desalination of the water or delivering the water to the farm. So this is an indirect cost because it is performed before we perform irrigation at the farm and is proportional to the amount of irrigation applied. That's why we talk about a variable energy requirement. In this equation, this coefficient C sub W is the energy spent per volume unit of water. Now we can simplify the previous equation for calculating the energy requirement of irrigation by putting together a component that is proportional to the amount of irrigation applied, and that would include the energy required for lifting the water, the energy required for keeping the operating pressure. This would include the efficiencies for the pump and the motor, and the coefficient of energy required for desalination and transport of water. Then we would have a component that is indirect and is fixed related to the manufacturing and installation of the irrigation system. We will see now an example of the energy requirement of irrigation as affected by the type of irrigation system or the quality of water. we are considering that the total amount of water applied during the season is 6,000 cubic meter per hectare. And we consider that we use sprinkler irrigation or drip irrigation using electric motors or diesel motors. The water depth is 50 meters. Here in the table we have assumed a pressure requirement of 35 meters for a sprinkler and half of that for drip irrigation. The indirect energy requirement for sprinkler has been assumed 8,000, while for drip it has been assumed 13,000. And here we have a coefficient that is the energy required for processing the water. For good quality water, this value would be 0, but for brackish water, a mean value of 7 megajoule per cubic meter has been assumed. Using this data and the equations that we have seen in the previous slides, we come up with energy requirements for good quality water or brackish water between 15,000 and 26,000 megajoules per hectare when the water quality is good, and between 57,000 and 68,000 megajoules per hectare per year, which is very high energy requirement when the water quality is poor, when we are using brackish water. It is interesting that there is not that much difference between using the sprinkler or drip irrigation system in terms of the energy spent if the total amount of water is the same. For many cases, however, with drip irrigation we can use water more efficiently, so the total energy requirement would be reduced as compared to what we see here. For rain-fed systems, the highest energy spender in agriculture is related to fertilization. The total amount of energy required for fertilization can be calculated using this equation. Here, NF is the number of applications of fertilizers and A is the energy consumption per application of fertilizer. So this is related, this is a direct component of energy expenditure. Then we have NA is the amount of nitrogen applied, kilograms per hectare per year, while CN is the energy required for producing and transporting each kilogram of nitrogen. The same goes for phosphorus and the same goes for potassium. Finally, we have a fourth component, which is the indirect component of energy spent in manufacturing, repairing, or maintaining the fertilizer spreader or injector over its lifespan. In this table, we show the mean coefficients for the equation that we have shown for calculating the energy invested in fertilization. The component related to the number of applications is 90, means that we spend on average 90 megajoule per hectare per application of fertilizer, and then we have coefficients of 77 megajoules per kilogram of nitrogen, and that includes manufacture and transport, and only 37 for phosphorus and 17 for potassium. It is clear that as the amounts of nitrogen are usually higher than the amounts of phosphorus and potassium, and the coefficient is also much higher, the main component for energy requirements in fertilization is related to nitrogen. Let's see an example of the energy requirements for fertilizing different crop rotations. Here we consider 3 different rotations under irrigation in southern Spain: sugar beet, cotton, soybean, barley, or rapeseed, maize. Here in the table we have the total amounts of nitrogen, phosphorus, and potassium applied to the first crop of the rotation, and the amounts of nitrogen, phosphorus, and potassium applied to the second crop. Here we also indicate the number of applications. For instance, for sugar beet we will apply almost 250 kilograms of nitrogen per hectare, around 50 kilograms of phosphorus, no potassium, because in this example we are assuming a soil rich in potassium, and we would apply for cotton almost 150 kilograms of nitrogen per hectare and almost 50 kilograms of phosphorus per hectare in 3 applications. Using the equation of the previous slides, we come up with a total energy requirement of 21,000 for sugar beet and close to 14,000 megajoules per hectare per year for the cotton crop. The average, in other words, the rotation values are 17,000 megajoules per hectare per year. If we consider a soybean barley rotation, now the amounts of nitrogen are reduced to only 20 kilograms for soybean and 36 kilograms for barley. The amounts of phosphorus and potassium are close to 30 and 37 for both crops, as you can see. Now the energy requirements is close to 3,000 megajoules per hectare per year for soybean and close to 5,000 for barley. The average is 4,000. For a rapeseed maize rotation, the amount of nitrogen is 98 for rapeseed, but the amount of nitrogen for maize is much higher, more than 300 kilograms of nitrogen per hectare. The amounts of phosphorus and potassium are 66 and 88 kilograms per hectare. And then we come up with values on average of close to 21,000 megajoules per hectare per year. We see that this rotation, rapeseed maize, has the higher energetic requirement for fertilization because of the large amount that we need to apply to maize of nitrogen. The second is the sugar beet cotton rotation because of the large amount of nitrogen that we require for the sugar beet. When we include a legume in the rotation like soybean, the amounts of nitrogen are highly reduced for both crops in the rotation, so the energetic requirements for fertilization are also importantly reduced. Apart from water and fertilizers, we need to use labor in the field for performing all the operations of agriculture. We can calculate the energy requirement for labor using this equation, with N hour is the number of hours required for a given operation in hours of men per hectare, divided by the workday duration in hours per day, multiplied by the embedded energy per person, megajoules per day. That means the energy required for sustaining and for the living of a human being. This is a quite obscure concept because it depends very much on the standards of living of the farmer. we put here values from 100 when we are under, let's say, less intensive agricultural systems, less developed countries, to 1000 megajoules per day when we consider farmers in very highly mechanized systems in well developed countries. Consider, for instance, if we harvest wheat using only labor, manual harvest completely. In this case, we can have, or we may require, between 500 and 1000 hours per hectare for the complete operation of harvest, cleaning, threshing, and so on. Assuming working durations of 8 hours per day and the embedded energy of 100 megajoules per day, considering less developed countries. In this case, the total energy required for harvesting the wheat is equal to the energy spent in the labor, would be between 6,000 and 12,000 megajoules per hectare. If we use mechanized system, then we only need 2 hours to harvest 1 hectare, and assuming working duration of 8 hours per day, but now increasing the embedded energy to 1000 megajoules per day, that means a developed country, the total energy required would be the energy required using the machine and the energy required by labor, which is 250, and the total would be 1400 megajoules per hectare. It's interesting to see that the total energy requirement is reduced when we use a mechanized system. Basically because the mechanized system is more efficient in producing, in performing all the operations required for harvesting wheat. But it is also interesting to point out that the calculations are very depending on the assumptions that we make about the energy required for a farmer to be alive for a day. That goes from only 100 up to 1000. In some cases, the requirement for grain drying might be an important component in the total energy requirements of agriculture. The equation that we would need to use for calculating this requirement would be this one, where Y is yield and CD is the amount of energy required for removing 1 kilogram of water. This coefficient is between 6 and 10 megajoules per kilogram of water that we need to remove. In the equation, Fw is the fraction of moisture on a wet basis. For instance, if we have a maize yield in terms of dry matter of 12 tons per hectare, and the initial moisture is 25%, and we need a final moisture of 17.5, the energy spent in drying using this equation would be 11,636 megajoules per hectare. So this can be an important component in those agricultural systems where grain drying is required. To calculate the total energy requirements of agriculture, we need to know the energy requirement of the different operations. In this table, we have a summary of the average typical energy requirements per operation of different tillage operations, primary tillage, secondary tillage, spraying pesticides, spreading fertilizer, sowing or harvesting. The less demanding operations are the applications of pesticide or fertilizer. Then we would have sowing, secondary tillage, and a lot of energy is required for primary tillage, for harvesting, in especial if we are harvesting underground organs. Apart from considering the inputs of energy to the agricultural systems, if we wonder about the efficiency of the system, we have to think about the outputs of energy of the systems. This is basically related to the energy content of the harvested products or the residuals if they are exported from the agricultural systems. In this table we have a summary of the energy content values per kilogram of dry matter in megajoules for harvested products, different types of crops, and residues. We see that typically the harvested part of crops does not exceed 20 megajoule per kilogram of dry matter, with the exception of those crops that accumulate oil, like soybean or cotton, oil crops like sunflower. With those we can come up close to 30 megajoules per kilogram of dry matter. In the case of residues, we are typically between 15 and 20 megajoules per kilogram of dry matter. So, to compute the total output of energy from the system, we multiply this energy content by the amount of harvest that we have. Let's see some examples. The first is a monoculture of rain-fed wheat with an average yield of 2.5 tons per hectare of dry matter grain and 3,750 kilograms of dry matter in straw. Applying the equations and the coefficients that we have seen previously, the total energy requirement for this system would be 14,700 megajoules per hectare per year, which we can decompose in 3,400 megajoules per hectare for operations, 9,600 for fertilizers, more than 1,000 for seeds, and more than 700 for pesticides. The most important component in this case is the fertilizer. If we are exporting grain and straw for the agricultural system, the output related to this amount of yield and this amount of straw is equivalent to 110,000 megajoules per hectare. So the ratio of output of energy and inputs of energy would be higher than 7 if only the wheat grain is exported. Then the ratio of output and input would be only 3.1. Now let's consider a rapeseed maize rotation with yields of rapeseed of 3,600 and for maize 12,000 kilograms of dry matter of grain per hectare. This rotation is irrigated using a sprinkler electric power system with a water table depth of 50 meters, and we apply a total of 6,000 cubic meters to maize and 2,000 cubic meters to rapeseed. The residues are left in the field. In other words, only the grain is exported. To calculate the total energy requirement, we have to first to find out the different operations performed in the field. For instance, for the rapeseed crop, we would apply the following operations: moldboard plow, 1 operation; disc harrow and cultivators, 4 operations; pre-plant fertilizer, 1 operation; applying a residual herbicide, 1; sowing, 1; applying post-emergent herbicide 1 operation, an application of nitrogen in as top dressing, and 1 operation of harvest. For maize would be almost the same, with the difference of less cultivator operations and 1 application of insecticides. Here in the table we write down the values of the energy required per operation taken from the tables. So the amount of energy required is obtained by multiplying the energy equivalent by the number of operations. For instance, 1 moldboard plow operation requires 1200 or close to 1300 megajoules per hectare for rape. Or for these harrows or cultivators requires for rapeseed a total of 1692 megajoules per hectare. We perform the same calculations now considering the materials. So we write down a table where we put the amounts of material applied to rapeseed and maize, 98 kilos of nitrogen to rapeseed, 337 kilograms for maize, for nitrogen, and the same for phosphorus, potassium, for seeds, for pesticides, and the total amounts of irrigation water. Here we write the energy coefficients, in other words, the megajoules required per kilogram of these materials, and using the equation that we seen previously, we calculate the energy required for irrigation water. And the total amounts for each crops are obtained by multiplying the amounts of materials by the energy coefficients for rape and for maize, and we calculate the average. We sum up the total for materials, and average is 36,400 kilograms. And for operations that we saw in the previous slide, 4,700. And the total amount exceeds 41,000 megajoules per hectare. See that in general the energy required for materials is much higher than the energy required for operations. In this case, the most important uses of energy are related to irrigation and are related to nitrogen fertilizers. The energy efficiency is calculated by considering the energy outputs for rapeseed or maize dividing by the energy inputs. The average efficiency of the rotation in terms of energy is 4.0. Finally, let's consider an example where we compare the energy requirements of rain-fed sunflower with intensive tillage versus the same crop with no tillage. Here we do the same. First we consider the number of the different operations like moldboard plow, this harrow, application of fertilizers, cultivator, sowing, cultivator for inter-row tillage, harvest or pesticide applications. And this is the number of operations when we perform tillage or we perform no tillage. When we perform no tillage, we now only sow, we harvest, and we apply pesticides. The fertilizer is applied during sowing. In fact, it requires more energy than the conventional sowing. Then the amounts of materials is different because in intensive tillage we don't apply pesticides, but we do apply 4 kilograms of active ingredient per hectare when we apply no tillage. The total energy requirement for intensive tillage is 10,000 megajoules per square per hectare per year, and close to 9,000 for no tillage. As we can see, even with no tillage, the savings in energy are not that important, because in grain-fed systems the highest investment in energy is related to nitrogen fertilizer, which in this case is taking more than 50% of the requirements of energy of the crop. Thanks for your attention.